Okay, we can start in a few seconds. Okay, so please go to Virtuale and download the new slides. Slide number 4. And please also download the material for collab number 2A and 3, if I remember well. Okay, so today we are going to see my solution about the construction of ensemble methods to solve the classification problem that we have introduced last time. But before showing my solution, I ask if you have complete or if you have done the the homework. And so if someone wants to show its solution, maybe, okay? And so we can discuss the solution, since I remember that I recall you that there is not a unique solution, the best solution. There are several solutions, and the difficulty in this field is to find the optimal solution, the solution that works well with the problem that we have. So here is the code of your colleague Lupo. So you can come here and show your solution of the transcription. Okay. Just the main things, main elements that you want to share with your colleague.
Okay. So basically,
Maybe it's better to talk on the microphone. Fai solo vedere I metodi che non ho collegato alla macchina. Va bene? Senza farlo andare.
Ah, ok.
Va bene, o lo vuole
sì.
far andare.
Ok, prima li descrivo. So basically, first I downloaded the libraries that I needed. In this case, they are Random Forest and Decision Tree. Then also I matplot because you will see that I use a graph to display one of the KPI to measure our accuracy, our classifier score. So then I didn't change anything here in this part because it's almost okay. So then, yeah, I have a problem with the triangles because in the first case, adding the triangles, the length of the list changed. So I applied this function to maintain the length of the coordinates within a certain range that is 800. So basically, going down to the main part that we are interested is this. So to do the debugging. So I don't know if there is already the shapes here. Maybe no.
I upload the file since it's in my computer. The shape 65.
So,
Thank you. connect also the machine. Oh, okay, the machine is already connected.
Okay. So basically, this is the results of the code. So basically, I create a function that creates multiple subsets, and it's here, begin. So we input the data and the number of models. In this case, the number of models is simply this integer here, so 50 model in this case. So that's are equivalent to 50 subsets, and the data are my dataset, and my dataset is a list that zip train X and train Y that are retrieved from this code here. So basically, creating a bucket models, so a list, I iterate through for the number of models, so for 15, and through a list comprehension, I randomly choose data to append to insert into the subset. So it's a list of different, so randomizing the data inside my dataset. And this creates a lot of subsets that will be appended into the bucket models. That is the list here. Returning, of course, the bucket model. So all the subsets that we created random.
I understand this part. Okay. So he's creating different subsets since he's applying the bootstrapping technique. Okay. Okay, it's similar to my part, and we will see that, for example, the for statement is not necessary since you can define the key values to sample the number of wanted examples, but it's okay.
Okay. This one, okay. So then to apply the classifiers, we need to separate the train X and train Y subset. So we create this comprehension. And then we also create the classifier subset that is a random forest. And we fit every train X subset, train Y subset that we created, returning the classifiers subset. So here we are evaluating the models. So we put as input the models eval X and eval Y, that in this case are taken from here, if I'm not wrong. Okay, where is? Okay, so for each element in the models and from each model, we use these accuracies. We create a list called accuracies to insert each accuracies that we will have from each models. So basically, after having applied all these things, so we have the model trained, it are 15, all accuracies of each models. And we can see that the mean of the average score is around 0.82, but this means changed based on of the number of subsets that we create. So I don't know, like if we change here, maybe we can put 20. We will have a different mean. I know it's the same. Yeah, but we have some subsets that have a really low scores. But basically, my idea was to train different subs models to understand if the classifiers improves with respect to the number of models what we input into the function. So I don't know, like maybe the more the models, the highest the scores that we will get in doing all the processes. So we can try again, maybe. Maybe we can see if the mean increased or not. Okay, no, it's always 82. Yeah, but I think this is also, it's also good. Like we know that with random forest the average accuracy is 82, so we can choose to have this classifier to use another type of methods, like I don't know, like instead of bagging, boosting, or not random forest, another one.
Okay, so this is an interesting solution based on bagging. So take inspiration from this solution. Also, I see that the code quality is pretty good since we use list comparison. That is a good way to perform operation in a single line in Python. I think that one part that can be improved is the merging of the outputs of the classifier, since the final prediction is not average on all classifiers, I think. So you have different prediction and then you average the score of different classifier. But one element that you can introduce in your code is to, for example, average the output of each classifier to make the final prediction. Okay. But it's okay. So thank you. And I can show also my solution is similar for a certain way, but different in the prediction, the final prediction. And okay, I connect the machine. Or this is based on bagging, since we have seen that maybe bagging is the most simple solution that we can have, we can implement here. And so, okay, upload. The code is pretty similar to the code that we have used the last time. So I'm run the usual, we can say, part code. Then here we open the shape.txt file. Here we shuffle the lines of the shape.txt file. And then here we define the train set, validation set, and also test set using 20%, 20%, and 60% in the test set. Okay, and then here there is my part about bootstrapping. So I remember the use of bootstrapping. And we start from a single training set. Okay. And then we divide the training set in many parts. in particular, I choose the value 3, but subset 1. And then subset 3. In my case, also in my case, like in the code of your colleague, it's possible to define the number of the subset that corresponds to the number of models, since we train each model on a different subset. So here you can see the code for to create the different subset. And also in this case, I use the method random choice. Since is very simple, you can perform random sampling with replacement. Okay. And in input, in the first parameter, I have the train set. In the second parameter, I can specify the amount of samples that I want to sample. Okay. And in this case, the amount is the length of the train set. So the total number of elements inside here divide by the number of subsets that they want to create. Okay, if here I have n elements, here I have n over 3 elements, of course. Okay, and then I perform a print to show the number of elements inside each subset, that is 53. Since originally we have 160 example in the train set. Okay, validation set, the testing set are the same, since we want to test our model on a single validation set and on a single testing set. Okay, only the training set is changing here with the bagging solution. Then I create the data that I use for the training of our classifier. In this case, I create what trains I call train X and Y, in which I append all the train set processed by the prepared data function. That is the function that creates labels and coordinates. Okay, the coupled coordinates and the label. And also in this case, I print the length, the number of elements in each subset. And as you can see here, the number of elements is different, since I remember you that we exclude triangle differently from the solution of your colleague, right? You include also triangle. So it's interesting also see these elements. And I think that if I remember well, you add the two fake coordinates, 0 coordinates, to match the length, the final length.
I don't know, but if you insert, you just delete, if you just insert the triangles in the code, then when you are going to go to prepare data, the length of the string is it gives you a value.
Yeah.
So I try to compress instead of increasing the length of the string.
Yeah, the number of features must fix it. So in the case of triangles, we have 6 features that are the 6 coordinates, while in all the other cases, we have 8 coordinates, so 8 features, and that is the problem. The problem that raised the error in your code. So in my solution, I exclude triangle. Okay, that was okay, but you can also include triangle. And if, of course, if you include the triangle, the problem is harder, since you have another shape to take in account in your code. Okay, and here you can see that I define a list of classifier, and in this list I append several decision tree classifier. Okay, so single decision tree classifier that I declare and then I append in my list. And in this case, the number of classifier is equal to the number of subset, as you can see here. So we have 3 different classifiers. Okay, so we have 3 subsets. 1, 2, and 3. And then now we have 3 different decision tree. Decision tree number 1, decision tree number 2, and decision tree number 3. Okay, this is the code is about this solution. Okay, and we are going to see the declaration of these 3 different classifiers. Okay, these are the subset and these are the classifiers, the weak classifier that we are going to train. Okay, where we train this classifier here. Okay, so we use the model fit as usual in scikit-learn. Okay, here I use this function. Maybe you can understand something, or maybe not. We're going to see this function is for iteration classifier data in enumerate what the zip of classifiers and our train subsets. Okay, it's a simplified version of the code that you can see here. Okay, so in iteration, what do I have in iter? I have the value returned by the enum function. So here I have 0, 1, 2, 3, and so on. Okay. And in the other two elements, I have the value returned by the zip function. Okay, so the couple create using the first classifier and the first training subset. In the following iteration, I have the second classifier and then the second train subset. And in the third iteration, I have the third classifier and the third train subset. Okay, and I put this information in this couple. Okay, is it clear? Okay, it is not about machine learning, but it's about Python programming. So, and note that in this data, I have labels and data. In the first position, I have data. So I have the coordinates. In the second position, I have the labels. Why? Since we use the prepared data function, okay? So to train my classifier, what I have to do? My classifier, CLF in this case, dot fit. In the fit function, have to use in the first position data, X, usually denote with the letter X. In the second position, the labels, Y. So in my case, the coordinates are in the first position of data. So I write data first position. And in the second position, we have the label. So I can write data 1. And so here I have the label. Okay. That is the explanation of the code that you can see here. Okay. So we have discussed the for statement, and then you can understand also the fit statement that we use here. Okay. And the output is that we have trained 3 different classifiers. You can note also this element. If you use the end parameters in the print function, you can define the ending characters of the string that you print on the screen. Okay. By default, this character is the backslash or something similar. Okay, is the letter N in this case. The meaning is that we go to a new line. Okay, this is the back character. Okay, so you skip all the white line, then you go on the new line in the following new line. That's why if you use 2 consecutive prints, you print the first line and then you print the second line. Okay, but if you change the final character, for example, in this case, I specify that I want the comma, then I don't have these characters, but the comma, and so the final output is my sentence, my first print, and the second print. That's why I obtain the output that you can see here, in which I have training the 0 classifier done. Okay, in a single line. Okay. So we have trained. Now we have trained this classifier, training, and then we have to test this classifier. How is possible to do that? So this is the training part. Okay. Then we have the validation or the test part. Okay, for simplicity, here we consider only the testing part. Okay, it's the same. We can apply the same procedure to the validation procedure and the test phase. Okay, but for simplicity, here you can see that I apply this procedure only on the test subset. Okay, it's not a test set, so it's not a problem. In this case, I have a single test set. Okay, with n elements. This part is different from the solution of your colleagues, so please be aware to understand this concept. And we have 3 different models, train model. So model 1, decision tree 1, 2, and 3. For each element of the test set, we want to obtain the output of each classifier. So we take the first element and we put in the first classifier. The same element is put in the second, and the same element is put in the third one, okay? And then we obtain the score prediction. For example, here we have the class, okay? Since the output for a classification problem is the class we have seen, okay? So for example, in this case, we have the class number, I don't know, 0. In this case, in decision tree number 2 output the class 0. Unfortunately, the decision tree output the class number 1. So we need a mechanism, an algorithm, a function that merge, for example, all these outputs. Since we want to apply, for example, the voting rule, okay? So the most voted class is the final predicted class, okay? Is one of the way to merge different output with ensemble method, if you remember the previous lesson. So what I've done here, I define a list of votes with 4 zeros, since we have 4 classes, okay? And then for each classifier called CLF, I use, okay, I take the first element of the test set. I need to reshape this element since I have to adapt the shape of the input element to the shape that want the classifier and input, okay? Is just a sort of bureaucracy of Python, since the shape is not one, since it's a single element, but must be 1, 1, okay? Is the same, okay? Only to match the input of the classifier. Then I get the single prediction. For example, I get the first prediction, second prediction, and third prediction. And then I use this prediction to update the content of the vote list. In particular, I increase the position indicated by the prediction, okay? So in this case, if I have this starting list, what I have to do here, number 0, so I have +1 here, 0 here, 1 here. So my final vote is 2, 1, 0, 0. I repeat, the meaning is that our classifier have specified output, have predicted output for 2 times the first class, the class number 0, for 1 time the class number 1, and 0 times the other classes, okay? The final step is to get the maximum vote. How is possible to do that? There is a function in in Python, very easy, is the argmax function, similar to the max function, okay? Argmax or max function. The output, if I apply the max function on this list, what is the output? 2 is the value with the maximum value, okay? Is the maximum value that we can find here. The argmax function returns the position, right? The position of the maximum value, okay? So it's very useful to use this function to find the best vote class. In this case, is 0. Since in 0 we have 2, that is the maximum value. And so the final prediction of our classifier is the class number 0. Okay. This prediction, I append this prediction in my final prediction vector that I use then to compute the score of my solution. Okay, so here you can see that I append my prediction, my final prediction, using the argmax function on the votes that I create before, okay? And then I can run the code, and you can see that, for example, in my case, the accuracy is 0.7. And if I remember well, my previous prediction using only decision tree classifier was about 0.6 or 0.5. using only one decision tree. Is a very simple classifier that we have seen together last time, okay? And so I managed to improve my final accuracy using an ensemble method. Okay? And I hope that this example can clarify to you the use of ensemble methods in your project or in similar project, okay? It's important to know how it's possible to program ensemble methods, since you can perform a lot of variation on this code, okay? You can define different classifiers, you can define different voting rule, you can define different training subset, okay? You are free to define many different variations. The same, you cannot do the same things with the pre-built method ensemble classifier of the scikit-learn package, since in that case you are forced to use the very they already implemented the mechanism in the scikit-learn packages, so you don't have the freedom to do what you want. Okay, that's why we have seen together two solutions of ensemble method. Okay. You can find this code on Virtuale, so please download it and study and try to also modify the code to obtain, or maybe also to improve similar the performance. Okay, to improve. You can obtain similar result or also improve the final performance. Okay, do you have question about that? How many of you did the exercise about ensemble methods? Okay, so raise your 1, 2. Also, I think you 3. Only 3. Okay, you can do better, since it's better to write code, okay, to pass the final exam, since you have to develop a project. So it's better to learn how to solve classification problem with programming language. Okay, so now we are going to see theoretical part about metrics. So download the slide number 4, and then we are ready to see the new parts, the new code of today. Is block number 4, okay? The block number 3 is not finished, is not ended, but now we skip to the metric part to see how it's possible to compute, to measure the performance of our training model. So this part is very important. And today we are going to apply to implement our methods to detect the performance of our training methods. So base metrics, or in other words, metrics that are pretty simple for the classification tasks. Remember that we are in the final step of our machine learning general pipeline. Okay, I remember you that in the first position we have data acquisition and data processing, and that contain all the procedures that we have to apply to data in order to prepare our data to be used in our solution. Then there is the model part, and we have seen a model based on pattern recognition or expert system solution, in which we have if then else statement or similar statement, and in which we don't have the training part, the learning phase, so we don't need training data. Okay? Maybe you remember the second laboratory exercitation. Then we have seen some model based on machine learning, and in particular, we have seen decision tree classifiers. We have seen SVM, support vector machine, and then last time we have seen ensemble methods, okay, AdaBoost and random forest. And also we have implemented our solution using ensemble method. The next part in model is deep learning, and we are going to see deep learning in the following lesson. today it's time to anticipate the prediction step that is very important, since in this part there is the output of our system. And remember that the output is the part of our system that the user see. So it's very important to have an output that is efficient, that is clear to our user. Okay, since our user or our customer use only the output of our machine learning system. And for us, it's important the output of our system also to calculate the performance of our system or our train. Okay. How is possible to compute the performance of our training model of our system? It's possible to compute the performance using metrics. There are several metrics, and there are some metrics that belong to the classification task, other metrics that belong to the regression task that we are going to see in the last part of our lessons, the regression task. And so it's important to know what metric apply on on the output of our model. Okay. Remember also that the computation of metric is important also for legal reasons, since the computation metric is linked to the achievement of certain contractual obligation. So it's very important when you define a contract to define also the performance of the system, since you know that if you paid a system a lot of money, you want that system works well. And how it's possible to define the level of quality of the system is possible. It's mandatory to define metrics that monitor the performance of our deployed system. Okay, so it's a very important part. So let's start with system performance with the classification task. Okay, it's the task that we have seen together until now. Remember that to compute metrics, so to detect the system performance, is important to have three ingredients. The first ingredient is the output of the model. Okay. The second ingredient is the ground truth annotation, is the label. Okay, is the annotation of data. Remember that we are in the supervised learning setting, so we are using annotated data, and so the second ingredient to compute metric is ground truth annotations. Okay, output and ground truth annotation. We compare, and that is the third ingredient. We compare the ground truth and the output of our model using a specific metric. Okay. One of the most used metric for our classification problem, and is also the metric that we use in our exercitations, is the classification accuracy. That is the percentage of correctly classified patterns. Okay. Here, in this case, patterns, like in the previous case, is a synonym for data points, data samples, items. Okay. So we have a certain amount of samples in our testing set, and then we want to compute the percentage of correctly classified patterns. And how it's possible to do that is pretty easy. We have to define a division between the patterns that are correctly classified over the total number of patterns that we have in our testing set. This is the accuracy. If we want to compute the error in a very easy way, the error is the maximum accuracy that we can obtain in our data, 1%, 100%, minus the accuracy that we obtain. Okay, so we can express the classification accuracy in terms of accuracy or error. Okay, pretty simple. Okay, so the classification accuracy is pretty simple, but you have to be aware about a problem that you can face. The problem is related with unbalanced classes, or rather, we have a testing set. In that testing set, we don't have the same number, the same amount of example for each class. For example, for the first class, we have 50 samples. For the second class, we have, I don't know, 80 samples. For the third class is a rare class, and maybe we can have only 5 examples. And this is a problem. And we are going to see why is a problem using this example. Imagine that we have trained a system that is able to understand if an image there is a cat or a dog. Okay, is an animal classification animal type classification system. Okay, so the input is represented by an image. The output, the prediction of the system is the class dog or cat. And then we have also the supervision. We have the ground truth annotation represented by the class cat and dog, of course. Okay. So in the first column, you see the predicted values, dog, cat, dog, and so on. And in the second column, you can see the ground truth values. Okay. So we can see that, for example, for the first 4 samples, we have a correct prediction, since you can see we have dog, dog, cat, cat, and dog, dog. Then we have a wrong prediction, since the predicted value is dog and then the ground truth is cat. And we have a second wrong prediction in the final part of our output. What is the accuracy, the classification accuracy of this system? Remember the equation that I showed you before. We have the number of correct classified patterns, so 5 plus 3, and then we have the number of the total number of example, 10. So in this case, the percentage accuracy is 0.8 or 80% of classification accuracy. And we can say that we have obtained a pretty good system, since the final accuracy is 0.8 or 80%. Okay. Now we can have a problem. That is the problem related to unbalanced classes. For example, you can see that we have the very same output. So the testing set is very the same, with the exception of the last prediction, in which we have a new class, the class mouse. Okay. So we can see that for dog, we have, I don't remember, 4, no, maybe 1, 2, 3, 4, 5, 6 different samples in our testing set. For the class cat, we have 1, 2, 3, 4 different samples. For the class mouse, we have only 1 sample. And of course, our system is not, for example, our system is not able to classify in the correct manner the class mouse. And then we have, for example, the predicted values that is cat. We can compute the classification accuracy of this system, and we found that we obtain a pretty good result, since, okay, we have 5 plus 3, so 8 over 11, since is the very same example of the previous example. We have only 1 additional sample, so the number is not 10, is 11. So 8 over 11 is about 73% or 0.73. Okay, that is pretty good. But maybe we might not realize that the system, for example, is not able to classify the new class, the mouse class. Okay. So the takeaway of this slide is, okay, it's okay using the classification accuracy, but focus on the fact that you have a balanced test set or unbalanced test set. Okay. Usually in the data set that you can download on the web, you usually find a balanced test set, but it's not mandatory to have a balanced test set. So if you are developing your own project, be aware to check if the test set and also the validation set is balanced or not. Okay. Question about that? Okay, everything was clear, I suppose. Another tool that we can use for our classification system is called confusion matrix. That is pretty important. Okay. The confusion matrix in particular is important or also fundamental for multi-class classification problems, multi-categorical classification problem, or classification problem in which the number of classes is more than 2. Okay. We can compute the confusion matrix also for binary classification problem, but we can say that the power of the confusion matrix is clear when we have multi-categorical or multi-class classification problem. In particular, thanks to the confusion matrix, we can understand how errors are distributed over our testing set. Let's see the example that I put here on the right of the slide. We have this matrix, and the classification problem is a digit classification problem. We have 10 classes that are the first 10 numbers from 0 to 9. And then we want to train our system, a machine learning system that is able to classify if the input values is 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay. In the rows of this matrix, we have the ground truth annotation. So we have the labels of our testing set. And that's why we have 10 different rows, since the number of the rows is equal to the number of the classes. The columns represent the predicted classes. Okay, so also in this case, we have 10 different columns, since the number of classes is equal to the number of columns, or vice versa. The number of columns is equal to the number of classes. A single cell so represents the percentage in which the system predicts the class, a specific class, with respect to a specific ground truth class. So, for example, let's see the first cell is the cell in the first column, first row. We have the value 0.46. The meaning is that our system is able to predict the first class in a correct manner with this classification accuracy of 0.46 or 46% of classification accuracy. Okay. Remember that in the columns we have the predictions, and in the y-axis we have the ground truth error. Okay, you can understand that very well, or we can say an ideal matrix, confusion matrix, should be diagonal, since in the diagonal we have the correct classification of our classes. So in the first case, we have 0 and 0. Okay, this is the diagonal. And this diagonal is pretty important, since here we have all the correct prediction. For example, the class 3 is predicted, unfortunately, only the 0.16% of the time which we have the 3 label as annotation. Okay, and if you go in different position and not in the diagonal position, you can have the distribution of the errors in our predicted class. For example, you can see that the class 0 is well predicted this amount of time, but you can see that the class 0 is often confused. That's why we use the name confusion matrix, since we can see the confusion in our classification prediction. The 0 class is often confused with the class with this percentage, 0.25. That is the class 6. Okay, So this is, for example, here is important to know this fact. And maybe we can understand also the behavior of our classification system. If we have the number 0, and then we have a number 6 that is in this way, this is written in this way, you can see that they are pretty similar. And that's why maybe we have the confusion between the class 0 and the class 6. Okay. Yeah. A very perfect confusion matrix has the value 1 or 1% in the diagonal and 0 in all the other cells. Yeah. If you obtain these diagonal matrix, you have solved in a very perfect manner the classification problem. Okay. Other questions about the confusion matrix? We are going to implement the confusion matrix today, so must be clear in your mind this configuration and also this tool. Okay. We have matrix also for regression, but we skip this part since we are going to see the regression task in the last part of the course. So for the moment, skip this slide. Okay, we have several formulas, but they are pretty simple. And also we have an example of regression, of course. Now we can introduce some advanced metrics, okay? Advanced since we can say they are different from the classification accuracy and the confusion matrix, okay? But they are pretty simple, so don't be afraid. Okay, if we have a binary classification in which the total amount of example is divided by positive and negative patterns to be classified, we can define 4 definitions. For example, we can have a true positive, also called TP, if a positive pattern is correctly assigned to the positive. Okay, a cat is assigned to a cat, for example. We have true negative if a negative pattern is correctly assigned to negative. Okay, a false positive, a negative pattern is incorrectly assigned to positive, and false negative, a positive pattern is incorrectly assigned to the negatives. Okay. These definitions usually are related to the classification problem that you are going to solve. With this classification, we can compute additional metrics. For example, we can define the true positive rate, TPR, that is the number of true positive over the total number of positive elements in your dataset, testing set. We can define also the true negative rate, that is the number of true negative over, I am in this configuration, over the number of negative samples. Then we have the false positive rate is the number of false positive over the total number of positive, and the false negative rate, that is the number of true negative over the total number of negative. Okay. The meaning of these metrics maybe are more clear if you think about the test of COVID-19, in which you can obtain also false positive results. For example, this is the same thing. You obtain, imagine that the test is a classifier that classify the virus inside your, I don't know, your body fluid. And okay, the prediction is you have COVID. Okay, you have a positive classification about the presence of COVID in your body fluid. But the ground truth is negative, since maybe you don't have the COVID. So in this case, we have a false positive prediction. Okay, and then you can derive all the other examples of this configuration. Introducing this notation, we can use this notation, this different notation, to define in another way the accuracy. Okay, so the accuracy can be seen also as the number of the total, the true positive plus the true negative over the total amount of samples, that is the sum between positive and negative samples. We can have also other metrics. Okay, so it's pretty important to define true positive and true negative, since we have, for example, the precision matrix that indicates how accurate the system is. The related question is what percentage of selected item is relevant. Okay, so that is the accuracy of the system, and also the precision, we can say. That's why we call this metric precision. And is the number of true positive over the sum between true positive and false positive. Okay. A second metric is the recall metric that indicates how selective the system is, or give an idea about the fact that the system is able to classify in the positive manner all the relevant elements. In this case, we can obtain the recall performance with the true positive over the positive, or in another way, we can compute the recall using true positive over the sum between true positive and false negative. Okay. Last two metrics that we introduce using false positive and true positive definition, and in particular using the precision and recall metrics. The first one is the F measure. The second one is a specific case of the F measure. So let's see the F measure. F measure is this equation, as you can see here. We have 1 plus beta to 2. And here we have a fraction in which we have precision multiplied by the recall over the precision plus the recall multiplied with the beta to 2. Okay. To compute the F measure, we have to define the value of beta. Okay. If we put beta as equal to 1, we define the so-called F1 score that is very used in our classification problems. The F1 score is 2, since as you can see here, the result of this equation is 1 plus 1 to 2, that is equal to 1 plus 1, so is 2. So we have 2 multiplied by with precision multiplied with recall over the precision plus the recall, since also in this case, beta to 2 is equal to 1 to 2, that is equal to 1. So this is the final equation of our F1 score metric, okay? F measure is a way to express precision and recall with a single value, okay? Maybe we want to measure the performance of our system using the precision, the recall. Maybe the comparison between different approaches is hard since we have two different values, and so the comparison maybe is hard since we have, for example, it is usual to find that the precision value is high, the recall value is low. So how is possible to compare different approaches using two different values? A solution is to use the F1 measure that gives in output a single score, weighting in an harmonic way the precision and the recall. So we have only one value to compare our trained system. That's why we introduced the F1 matrix. That is pretty important. Okay, here are some recommendations to compute the matrix. We have already seen this part, but it's very important, so we are going to repeat it another time. You have to remember the distinction between training, validation, and testing set. That you have to use, you are forced to use, you must use the training set to train your model. The validation set is used to define the parameters of your model. For example, you declare the SVM methods. And if you remember, around the brackets of the SVM, you have many parameters. Okay, how is possible to choose the best parameters? You can test several times the train classifier on the validation set to see to find the best configuration of the input parameters. Okay, this operation must be conducted on the validation testing, the validation set. Sorry. Okay. And then you use the testing set to measure the performance of your model. So you apply the metrics that we have introduced today on the output of your model obtained on the testing set. Okay. It's very important that the testing set and also the validation set are disjointed with respect to the training set. Okay. So an element cannot be in the same time at the same time in the training and in the test set. Okay? But all the elements of the testing set must belong only to the testing set, the same for the validation set, and the same for the training set. Okay. And the problem is when the training set is problematic. So we have a very reduced amount of, a limited amount of training sample. So it's hard to define a proper validation set. So it's hard to understand when the model performs well or not using the validation set. The solution is to use the key-fold cross-validation that we have introduced in the second or third lesson. Okay, so if the validation set is too small, the model evaluation, the evaluation about the hyperparameters, the input parameters of your model will be imprecise. So you can apply the key-fold cross-validation. Okay, how it's very simple to be implemented. So we can see another time how it's possible to implement the key-fold cross-validation. You have to define the parameter key. Okay, key is a number. Okay, for example, we can define 3, and then the training data are divided in 3 different subsets. Okay, if we select key equal to 5, we divide the training data in 5 different subsets and so on. Okay, in a very similar way to what we have done here. Okay, but with the validation set, not the training set. Okay. Then we can use, as you can see in the image, we can use one fold for the validation, one fold for the testing, and all the other fold to train our model. And then we can repeat this process using every time a different fold for the training and also the evaluation of our trained model. Okay. So remember, if you are using a very small data set, you have downloaded a data set in which there are, I don't know, 100, 200, 500 of different samples, you have to apply this technique in order to obtain a proper validation set, a validation set that you can use in an efficient way to understand if your model is trained well or not. Okay? Clear? So. Okay. So we can have a 5-minute break, no more, and then we are going to see the new part of the code of today. So remember to download the code number 3, classification with machine learning classifiers and feature descriptor. Okay. See you in 5 minutes.
Yeah, because I need it.
No, I don't have a line. Quindi ci dice penso se a volume. Cioè non ho la parte d'ora che no, allora io lo prendo alle 4, però devo prendere le istruzioni quindi devo arrivare inizialmente in una allora io sono dalle creatività poi dopo Ale lupo si dopo perché ha un prodotto da veramente quindi e resta a parlare prima cioè tu da questo è data si prende lo so se non so Oh, no. It's a really this is definitely Russian ethnic. It's
Okay, we can start the code part of today. Okay, so open the code on Colab as usual and try to connect the machine, the virtual machine. And if you don't have the Euclid dataset, please download the Euclid dataset from Virtuale. And you can keep the zip version, the compressed version, since we are going to upload the zip file, and then we are going to zip the file in our virtual machine, okay? So let's start. As you can see here, we are going to see the code to solve the problem of classification with machine learning classifiers and feature descriptors. If you remember, we have seen two different feature descriptors in the last lesson. In particular, we have seen two feature descriptors that we can apply to images in order to get discriminative features, discriminative representation of our images. There is a nog feature that we can use to compute the shape of the object inside our image, and the LBP feature that we can use to describe the texture of elements inside our input images. Okay, we have seen only two feature descriptors. Of course, there are a lot of different feature descriptors that you can find on the web in the literature, but we only see these one since they are pretty useful, and I think that we can use this. You can use these descriptors also for your project. Okay, so we start our code importing the libraries as usual. So we import the sklearn library, the NumPy library, and also, as you can see here, we are going to import also the confusion matrix method from the sklearn library. So we are going to use our the confusion matrix to see the performance of our model. Okay. And then, okay, the other packages, in particular, in the schemage package, we found we can find the implementation of the feature descriptor called OG, that is the OG feature descriptor, and the LBP feature descriptor that stands for local binary pattern. Okay. At the beginning, we can also define our seed, okay, is the NumPy random seed. We can use this seed to have deterministic experiments, okay? It's important since, for example, when we apply a random function, for example, we apply the random shuffling on our training data. We want to run multiple times our code. We want to have comparable results. So it's important to define a random seed in order to have reproducible experiments. Okay, so remember to define a random seed. Okay, you can specify the value that you want in the bracket. Okay, as input argument. And in my example, I insert the code 1821. Okay. Here we have the get label function that is similar or the same that we have of the get label function that we have seen before. So I skip this explanation. And then we have the extract features function. Okay, that is very important. In the first position, we have the images. In the second position, we have the feature type. In the third position, we have the image size. So we create two different lists, one for the labels and one for the features. And then for each image that we pass to the function, what we do, we open the image in this way using the imread function. Is the OpenCV function that we have seen in the first or in the second lesson, don't remember well. The part about the images, the use of images in our code is possible to handle images using the OpenCV library, and the imread command can be used to open an image in our code. Okay. And with the 0, we specify that we are opening this image in gray level color. Okay. So this image has only one matrix. Okay, not 3 different matrices, but only one matrix. Then we use the resize method, always in the CV2 or in the OpenCV package. With the resize method, we can resize the image, the spatial resolution of the image, to a given image size. Okay, in this case, we have a square input image since we use the same dimension for the X and for the Y, for the column and for the row. Okay. And then here, if we have selected the feature type equal to OG, we apply the method OG that we have imported from the schemage package, in which in the first position we have the image on which we want to apply the OG. And in the following position, we have other parameters. If you remember the slide about OG, you know that the OG is computed not on the whole image, but the whole image is divided into a block, and each block is divided into cells. And for each cell, we compute the orientation of the gradients, and the number of orientation that we compute is these parameters. Okay, and finally, we create a unique histogram with all the orientation that belong to different blocks inside our image. For the LBP, we compute the local binary pattern. We specify the radius and the number of the points that we want to take in account for the computation of our local binary pattern. And I use the reval command to transform the output that is 2D in a 1D vector that we can use in our system. We have also a third type of feature that is called image. Okay, the abbreviation of image is IMG. In this case, what we have done here, we just unroll the image. Okay, we use the reval command. You can search the documentation of the reval command, but the reval command receive, for example, a 2D input, and the output is a 1D vector. Okay, is an unrolling method. Okay, imagine that you have a matrix. Is an image, a gray level image, so we have only one matrix. We have a spatial resolution of 3 times 3, since we have 3 blocks and 3 blocks, 3 cells, sorry, and 3 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9. The reval command means that we can have, this is 2D. We have a 1D output in which we have in the first position, the first block, the first pixel, sorry, cell. In the second position, the second pixel, third position, and so on. until, in this case, the pixel in the 9th position. Okay. So in this case, we are not applying a real feature descriptor, but we just provide an input of our system and a raw image as is. Okay, and that can be problematic since the spatial resolution of the image can be very high. Imagine if we have a, I don't know, a 4,000 times 3,000 image, the number of the final parameters if we compute this operation. Okay, it's pretty high. That's why we introduce the features descriptor. Okay, so I can run this cell, and that's all for now. Okay, so now for data, I unzip the content of the Euclid dataset folder. And so I tell you to upload. Okay, I already unzip the content of the folder, so it's better to stop the. But you have to run this cell in order to obtain the unzip content of the zip folder. Okay, and in particular, the zip is here, in which we have the rectangle, rhombus, square, triangle folders, and our shape.txt file. Then we create the list of our images using the glop and join command. We have already used these commands, okay, to find all the path of our images. In this case, we use this command in combination with this statement. That means that we want to select all the PNG images inside our folder. And since we have 4 different folders, and in each folder there are 200 images, the total number of images is 800. Okay, now we can start the training phase. We have to divide our data in training, validation, and test set. In this case, I use 60% of data in training, 10% of data in validation, and 30% of data in the test set. And also remember to shuffle your dataset, since it's important. For example, since in our dataset, all the images in the first positions are belong to the triangle class. Then we have the rectangle class. Then we have the square class. So it's important to shuffle to the dataset in order to have different samples. Okay, and I can run. And as you can see, we have 480 samples in the train, 80 in the validation, and 240 in the test set. Then here I extract the feature descriptor. I decide to use, for example, an image size of 112. And for example, here I decide to use to compute the OG feature. And then I extract the features on the train set, validation set, and test set. This function, extract features, is the function that I showed you before, okay? So in input, I receive a collection of images, and for each image, we open the image, we resize the image, and then we compute the feature descriptor specified in the input parameters. And there is also the TQDM command that show you the progress bar for the for statement. It's very common to use this command to see the speed of the process. As you can see here, if I run the cell, you can see that we have a progress bar that reports the percentage of processed data. In Python, it's very easy to obtain this process bar since you have to use only the TQDM command, okay? And then we have done. We have compute the feature descriptor or on all our data. Training data, validation data, and testing data. For classifiers, we can specify, and we know that there are several classifiers that we can use. In my case here, I specify an SVM, a support vector machine classifier, but your code, in your solution, you can specify a decision tree classifier, random forest classifier, another boost classifier, and so on, okay? In this case, we are going to use SVM. What about the training? The training is the same as in the previous exercise, but you have to remember that in this case, in train X, we don't have the coordinates, we don't have the images, we have the features, descriptors that we have compute before. And then I can fit my model. And then I can see the validation score with my train model, okay? Remember the difference here with the fit method, I pass the train X and train Y, while with the score method, I pass the validation data set, so testing set, sorry, the validation subset, so val X and val Y. And here I can see that the classification accuracy of my classifier is 0.73. Okay, in this case, for example, I can change the parameters of my SVM, I can change the image size, I can change what else? Here, the parameters for my OG feature descriptor in order to find the best performance of my solution, of my implemented algorithm. And then I have to, for example, change these parameters and then run another time the fit function and the score function on the validation set in order to define the best parameters of my training model. When I have done, I can test my model on the testing set. In particular, I use the predict function, the predict method that give in output the class of the predicted samples. In this case, we have 240 different samples, so we have 240 predicted classes. And finally, like in the previous examples, we use the accuracy score that computed the final accuracy. Now, you know in details what is the accuracy score function, what is the meaning of the accuracy score that I show you today. So in our case, we obtained a final accuracy of 0.72. That is, I think, a pretty good accuracy since we are using images, okay, not coordinates. What about the confusion matrix? We have today we have seen the use of confusion matrix to see the performance of the training model on multi-class classification problem. In our case, we are in a multi-class classification problem since we have 4 different labels. So we can use confusion matrix to understand the performance of our model in detail. It's pretty easy to use the confusion matrix since you can find all the tools on the method on the scikit-learn package. So as you can see here, we have to build our confusion matrix using the ground truth prediction and the predicted classes. Sorry, the ground truth labels and the predicted classes. Okay. Remember the 2 ingredients that we need to compute the matrix. So the output of our system and the annotation of the data that we are using. And then we can print the matrix. And I can show you the results. Okay, there is also the graphical representation of the matrix, but you can see here there is a textual, we can say a textual representation of the confusion matrix in which we can see that we have 4 columns and 4 rows since in our problem there are 4 classes. And as you can see here, the system is pretty good since in the diagonal we have the highest score. In this case, is not the score, is the number of samples correctly predicted. Okay. if you want the score, you can apply, for example, this function in which we take the diagonal of the matrix and we divide each element of the diagonal of the matrix with the sum of the row of the matrix. In this way, we obtain the percentage. For example, in the first case, what is the meaning of 53? The meaning is that our model is able to correctly classify the first class the 80%, about 80% of the time. Okay. In the second case, in the fourth case, for example, we have 48 samples correctly classified. As you can see here, we have a very low level of confusion, and that's why the probability, the score of the our trained model on the fourth class is 0.94%. That is pretty high. In scikit-learn, you can find also a method to display in a graphical way the confusion matrix. And it's pretty simple. You have only to import the confusion matrix display method that in input receive the confusion matrix that you have built using the predictions and the ground truth labels. And if you define the confusion matrix display and then plot this confusion matrix, you can obtain this graphical representation of the confusion matrix. That is pretty useful since you can understand the performance of the method also using colors. And as you can see on the right, blue colors denotes low performance, yellow color denotes high performance. That's why on the diagonal, you can see that we have yellow color and similar to yellow color, light green, light blue, and so on. When you have 0, we have blue color or purple color, or I don't know what color is. Okay. Do you have a question about this code? I suggest you to download the code and has homework to play with this code to see how it's possible to define different feature descriptor. Remember that we have defined different feature descriptors, so you can change these parameters. And so you can see the performance of the method using OG, LBP, or the unroll image. You also can change these parameters, and you can see that the computational load of your algorithm change a lot. You can specify a very big image size, and then you can see the difference between using a big image size or a small image size. Again, you can define also, you can use other parameters for your OG, okay? It's not easy to, there is not an optimal value, an optimum value of for LBP or OG, but you can try different parameters in input. So this is the first homework that I give you. So try to use different classifier, different feature descriptors. You can see differences in computational load and in performance. We are going to discuss this aspect in the next lesson. The second homework is to compute your own confusion matrix and also the diagonal scores. So in the previous case, we have used the method of the scikit-learn package. Okay. In this case, you have to write your own algorithm to compute the final confusion matrix. Okay. I will open on Virtuale an homework so you can write the code and upload the code on Virtuale. Okay. The third homework is the second, so since we consider the first to change the code as first homework, if you want, it's not mandatory, this homework, you can download the Cypher10 dataset from Virtuale. I will upload the Cypher10 dataset from Virtuale, And you can try to solve the classification problem using the method that we have seen before. In the Cipher-10 dataset, you will find images, okay, of digits. And so the classification problem is, the problem is to classify the different digits that you receive in input. It's a good exercise in order to see if you have understood every element of this code, okay? As I report here, the Cipher-10, for example, consists of very small images. We have 32 times 32, so very small images, color images. So in this case, remember that you can decide to work with RGB or gray level images that are divided in 10 classes. And in particular, I will put 300 samples in the training and 50 testing sample in, of course, in the testing set. Okay. So for today, we have finished. If you have questions, please tell me. If you have doubts or questions during the week, I suggest you to write me an email so we can define an appointment. Okay. So we can discuss other details about the code. We can discuss other aspects about the slides and so on. Okay. So you can use me to understand your doubts, to explain your doubts. Okay. See you next time.
Non riuscì a seguirla.
Sì.